So this is the lecture video for experiments 8 and 9, and that is going to comprise the synthesis of a precursor of Prozac. So just to give you a little bit of a background on what Prozac is. So Prozac is representative and probably the original and most famous example of a class of drugs called serotonin-specific reuptake inhibitors, or SSRIs. This class of drugs is primarily used to treat depression, and to piggyback on top of the lecture discussing combinatorial chemistry and the discussions of the synthesis of topical anesthetics that were derived from the molecule cocaine, Prozac is another example of a class of drugs that had their root in an understanding of how cocaine worked. And if you want sort of some more interesting trivial knowledge, is that before Sigmund Freud became known as the father of psychoanalysis, his original theory that he had built his career on is that a variety, if not a majority, of psychological conditions could be treated through extensive use of cocaine. And while that may seem funny now, that actually was the basis for how we now treat depression with this class of SSRI drugs. So I think I've mentioned this before in an actual lecture, is that the mechanism by which cocaine works is that it's a broad spectrum neurotransmitter reuptake inhibitor, including it being a serotonin reuptake inhibitor. So the original work trying to understand the link between depression and low levels of serotonin really had at their root an investigations to understand how cocaine worked. And so, really, if you think about the origin of our current day treatment of depression, it really has its roots, again, with Sigmund Freud using cocaine. So a couple of logistical items. This says that it's a 3-week synthetic sequence. We are only going to do experiment 8 and experiment 9. So we are going to perform the Monish reaction, and we are going to perform the sodium borohydride reduction of a carbonyl. We will not be doing the nucleophilic aromatic substitution. So before you come, and the other thing to bring up is that I have sent a couple emails via Blackboard that the reaction sequence has changed a bit. That on Wednesday the 27th we will actually be doing the synthesis of nylon. On Thursday the 28th we will be doing from 1:30 to 4:30 the Monish reaction, and then if you're staying on that Thursday evening, you'll do the reduction of the carbonyl. If you're going to go to the Friday afternoon session, that's when you'll do the reduction of the carbonyl. So the first few lecture slides are actually going to look pretty familiar to you. The only thing that I want to bring up here is that if your Monish reaction does not work, you're going to have to repeat it. And it is a pretty straightforward reaction to do, but if you don't get product from experiment 1, you're going to have to repeat it to have material to go through the sodium borohydride reduction. So this is very important. So consequently, take care and do your best work for making your Monash product. So the slides that I'm saying are that should look a little familiar are this idea of selectivity in organic synthesis. And there's a few types of selectivity that we're going to be talking about. We're going to be talking about chemoselectivity, regioselectivity, and enantioselectivity. And all of these are relevant in this particular reaction. So again, to reiterate these slides, is that if you are going to perform a reduction and you wanted to reduce a ketone to an alcohol, sodium borohydride is a completely appropriate reagent that you could use for this. You could also use a reagent like lithium aluminum hydride to perform this reduction. So in terms of chemoselectivity, there's not much in terms of chemoselectivity regarding sodium borohydride reducing ketones versus lithium aluminum hydride reducing ketones. However, if you have a carboxylic acid derivative and you want to reduce that to an alcohol, and then also the pendant ester group being hydrolyzed, this reaction, on the other hand, will only work with lithium aluminum hydride. If you tried to use sodium borohydride here, so if you tried to add if you tried to do this reaction with sodium borohydride, the reaction would not work. So this is an outstanding example of chemoselectivity in the context of a carboxylic acid derivative, that lithium aluminum hydride will reduce this down to the alcohol plus the pendant ester group, but sodium borohydride will not react with this at all. Probably a better example of this is in the case where we have this aromatic system where we have two functional groups, both a ketone and a nitro group. If you treat this ketone with sodium borohydride, it will effectively reduce this carbonyl, or this ketone, to the alcohol, but it won't touch the nitro group. Another reducing reagent that you can use is just tin metal in hydrochloric acid. And even though that this is a reducing agent, that it only reduces the nitro group to the aniline. So this is a really good example of chemoselectivity. Now we talk about regioselectivity and when we have a reaction. So if you remember back to the first couple weeks of your organic lecture class, this is typically the first reaction that's taught to you. So if you think about how we add HBr over a double bond, we get something like this. And then if we think about where is the carbocation going to form, you have two choices. It can either form on the primary carbon or the secondary carbon. Hopefully everybody remembers that secondary carbocations will be more stable than primary. So in this case of adding HBr across this double bond, we would preferentially obtain this secondary bromide instead of the primary bromide. And then hearkening back to Chem 233, when you go through the elimination of this alcohol to form this carbocation intermediate, then this carbocation intermediate can eliminate either via losing this hydrogen ion or this hydrogen ion to form a variety of products. You can get the trans 2 olefin, the cis 2 olefin, or the terminal olefin. And hopefully you'll remember that this is going to be the preferred product from this type of elimination, but you will in fact get both of these. The final example of selectivity that we want to talk about is this idea of enantioselectivity. So this can take a couple different routes. So if you think about your SN2 reaction, so under SN2 conditions, that if you start out with a chiral bromide, you are going to get a chiral product out. And the reason that you get the chiral product out is defined by the fact that this nucleophile undergoes a backside attack, which is dictated by the molecular orbital systems of how this particular molecule reacts. So if you start out with a chiral bromide, you're going to end up with a chiral alcohol. On the other hand, if you do this under SN1 conditions, you're going to get, draw that perfectly, so that carbon refers to this carbon. You're going to get this carbocation, and remember that that carbocation is going to be sp2 hybridized, right? Because there's no electrons in there, so that carbocation is going to be an unhybridized p orbital, and consequently, when the Br comes in to react, negative charge here. When the Br comes into react, because that's sp2 hybridized, there's no difference whether it comes in on the C or the reface. So consequently, the product of this reaction is going to be racemic. The other example is from a reaction that you just completed, and that is many times you can take an achiral starting material and then obtain a chiral product out of this. So when we took ethyl acetoacetate and exposed it to yeast, and the alcohol dehydrogenase enzyme reduced this terminal ketone, then we obtained a chiral product from an achiral substrate. And this is going to become important when we look at previous syntheses of Prozac, is that Prozac is the original form of Prozac was a chiral molecule, and so consequently it was important to identify synthetic routes that could take advantage, or it could generate a chiral product out of this. So the final thing to talk about in this idea of selectivity is that when you talk to people about designing synthetic routes, they really do spend a lot of time talking about this idea of the art of organic synthesis. And while that may seem a little bit esoteric based on your exposure so far to the chemistry in 233 and 234 lab, is while that may seem a little esoteric based on the exposure you've had thus far, I will say that when you're designing a synthetic route that's going to take 10 to 15 linear steps, in a case like that, being able to save even just one step could mean the difference between a molecule going forward and becoming a drug, or going nowhere and just ending up as a paper in the literature. So that's a very important thing to remember, is that when you're actually trying to make a molecule for a commercial purpose, that the synthetic routes really do have to be efficient, because if you're making this molecule for the world population, you're going to be forced to make metric tons of this molecule. Alright, I'm actually going to break this lecture up into two parts at this point, because I'm having a little bit of trouble with my video editing software. So I'll pick up right here on the second video.